Hello, my name is Brandon, and welcome to the next video in my series on basic statistics. If you are new to the channel, welcome, please subscribe. If you're a returning viewer, it is great to have you back. If you like the video, please give it a thumbs up and share it with classmates, colleagues, or friends, or anyone else you think might benefit from watching it. So all that being said, let's go ahead and get started. So this video is the next in my series on simple linear regression, and it is an important one. In this video, we're going to talk about understanding model error. So understanding error in regression is absolutely fundamental and crucial to gaining a really deep understanding of what's going on in regression, how we can build better models, and actually understand what the output is telling us when we run regression in Excel or Jump or R, whatever it is. Understanding exactly what we're looking at. And I'm going to do that in as visual a way as possible. There'll be a little math in here, but nothing difficult. So let's go ahead and get started. So this video is brought to you by the great people at the Great Courses Plus. If you're watching this video, chances are that you need to or want to learn something. And there are few better places to learn things than the Great Courses Plus, where you can access over 10,000 video lectures on almost any topic you can imagine. So look at the description below, click the link, and help out the channel here, and of course the Great Courses Plus. So let's go ahead and get started on looking at understanding regression model error. So just a quick refresher, here is the data we've been using. If you are new to the channel or the video series, I'm not going to go into great depth, but we're looking at data that involves the bill or meal amount at a restaurant here on the x-axis, and then the tip amount the waiter or waitress received over here on the y-axis. We have 6 data points, not a big data set. So you can see that a bill of $34, the server got a tip of $5, so on and so forth. The average bill was $74, and the average tip was $10. So here is our regression equation. Y equals 0.1462x minus 0.8203. The numbers might be a little bit different depending on what you use. So I think I used Excel for one and maybe Jump for another one, but they're basically the same thing. So our slope is 0.1462. Our intercept, which you don't really pay attention to in this case, is negative 0.8188 or 8203, depending on which one you're looking at. The centroid, which again is the mean of each variable, is 74. And 10, which will be important in other analyses. So here is our graph of our regression line and our data. So what that means is for every $1 increase in the bill, we would expect or predict an increase in the tip amount of about 15 cents. Technically, it's 14.62 cents based on our slope, but we'll round up to 15 cents. So total sum of squares. This is the beginning of really understanding what's going on when we want to understand model error. So remember, when we find the total sum of squares in a regression model, what we're doing is looking at how far each data point or observation is from the mean of the dependent variable. In this case, it's y bar, which is the actual tip amount. So remember, the y bar or average tip amount is 10. So that is represented by this line. Here on the graph, you can see that dashed line going across at 10, and we're looking at our sum of squares equation up here at the very top. It's very simple math, don't freak out. The y bar is also 10. So the 10 represents that graphically, and the 10 is there in the equation up here at the top. Now remember, y sub I is just the observation. So whatever our regression equation predicts, we would just go ahead and put that in for yi, and then we would go ahead and do our sum of squares, which we'll do here in a minute. But y bar is just the mean of the dependent variable, which is in this case 10. So we call those residuals. So if we look at here on the left at meal number 1, the amount is 5 off of the mean. So it was $5. The mean is $10. So the tip was $5 below the mean. The residual is negative 5. And then when we square that, we get a value of 25. So when we're talking about total sum of squares, what we do is we take each residual, so how far each data point is from the mean of the dependent variable, in this case 10, then we square it, and then we add them up. That's all in simple regression that total sum of squares is. So here is the actual output if we run this in a software package. So there's a lot of things here, and we're not going to look at all of it, but I do want to point out several things that are important for understanding error. So the first thing I want to point out here is this error block here on the lower left. So you can see that we have error, we have total, and the first thing I want to point out is the total sum of squares, 120. Well, where did we see that before? We saw that in the previous slide. So our total sum of squares that we calculated in the previous slide is confirmed here in the actual output. So 120 is the total sum of squares. The next thing I want to point out is the error sum of squares, or sum squares error. In this case, it's 30.07489. And then the mean square, or MSE, is 7.5187. And if you're freaking out about all the numbers and where they come from, don't worry. We are going to get to all that and how they're calculated and things of that nature. But when we're looking at the error, we're focusing on this part of the output. Total sum of squares, or sum of squared due to error, and then the mean square error. Okay, and we'll figure all those out here in a minute. But also notice that, of course, the model sum of squares of 89.92 and so forth, and the error sum of squares of 30.07 and so forth, those add up to our total sum of squares here at the bottom. Then we have this thing called root mean square error, or standard error. And that will become important here in a second as well. But basically, it's kind of how well the data points or the observations fit around our regression line. That's the best way of thinking of it. Now, this is called different things in different software. Sometimes it's called root mean square error. Sometimes it's just called standard error. There is no universal way, unfortunately, like many things in statistics, of naming things or using notation. The general pattern of output is the same in most software packages, but just note that it could be called something different. So let's talk about our sum of square error. So here we have our graph, a little bit different. So here we have our regression line, here the black line. The purple values are what our regression equation predicts for that value. So you can see here that I think here in the third value up, we had a bill amount of $64 here along the x-axis. And we had like a tip of like $11 and something like that. That's that orange diamond there, the third orange diamond. But our regression equation predicted something less than that, a little bit over $8. That's the purple dot. So what we have is the difference between what the regression equation predicted, the purple dot, and what our actual data observation was, which is the orange diamond. So that's the difference we're looking at here. So when we go ahead and look at how far each one is away, okay, again, a measure of distance, in this case, dollars, this is what we get. So for the third data point, we can see that the distance between what our model predicted, the purple dot, and what our actual observation was, the orange diamond, was 2.46 dollars. Okay, that is our error, or the difference between the two. So again, what we do is we take those errors and guess what? We square them. So when we go ahead and square those errors, we're going ahead and doing this here, what we get is our squared errors. And it literally means that. We're taking our errors and squaring them. So the distance between what the regression equation predicts, the purple dot, our observation, which was the orange diamond, what our observation was, and then we square that difference. Those are literally our squared errors. So SSE, or sum squares due to error, is literally the sum of the squared residuals, what we just saw in the previous slide. It's a measure of the variability, so how far those observations differ from our regression equation. So the fancy way of saying that is the equation we had before. So SSE equals y sub I minus y hat sub I squared. Now, remember, in total sum of squares, it's almost the same thing, but instead of the second term being y hat sub I, it is y bar, the mean. So in total sum of squares, that's the only difference. We take the difference, square them, and then sum them up. So that's actually what we did. So we took those sum of squared errors that we did on the previous slide or two, and we add them up, and we get a sum squared due to error of 30.07489. So remember that number. So if we wanted to, we could actually calculate that very easily in Excel or something else. So we're going to calculate the SSE actually by hand using Excel. So here's what we have. Okay, just an Excel sheet with some very simple formulas. So don't freak out. So here's the SSE formula we had before. So y sub I minus y hat sub I, difference between the actual and predicted, squared, summed them up. So here's our y sub I, that's our tip amount. That's all that is. Our y hat sub I actually comes from our regression equation. So all we did was take our regression equation and we substituted the bill amount into that equation and it spits out a predicted tip. Okay, that's basic regression. Then we subtract the two, that's our residual. So the observed value minus the predicted value determined by that regression equation on that line. Simple subtraction. Then we take it and we square it. And then we add them up. Tip amount minus predicted tip, we square it, sum them up, and that's SSE. Okay, so this is what we get when we actually do it in Excel. And I did notice just now that there is a typo. Squared residual. I guess that's the country in me. Sorry about that typo. But going forward, we take the tip amount, y sub I, minus the y hat sub I, which we get from the regression equation by inserting the bill amount. Then we go ahead and subtract, square, add, and that's what we get, 30.07489. So you can actually see the numbers work out. So let's talk about mean square error. So a little bit of text here, but it's important to understand. So the mean square error, which we saw in the output before, okay, or S squared is the notation, is an estimate of sigma squared. Okay, so remember sigma squared means variance. That's from way back in the beginning of the stats course. We learned about sigma squared variance, and then sigma is deviation, and so forth. So MSE S squared is an estimate of sigma squared, the variance of the error. And we talked about error in the previous slides. In other words, how spread out the data points are from the regression line. That's sort of the lay way of thinking about it. So MSE, the mean square error, is just the sum of squares of error divided by its degrees of freedom, which in this case is 2 because we are estimating the slope and the intercept. So in simple linear regression, the degrees of freedom are always 2. In multiple regression, it might be different, but in this case, it's just 2. So here we are. So MSE, or S squared, is equal to SSE divided by n minus 2, degrees of freedom. So again, we divide by n minus 2 and not just n. So remember, we're using sample data, not population data. So that's why we use the different notations. It's also why mean square error is a bit of a misnomer, because it's simply not the average of the residuals or the errors. So mean, it's not really, we're not actually averaging all the residuals out. So if we were using population data, we would just divide by n, and it would simply be the average of the residuals. But again, since we are using sample data, we have to build in degrees of freedom, which in simple linear regression is always n minus 2. Okay, so standard error of the estimate. So we'll get back to MSE and SSE as we progress. So the standard error of the estimate, or sigma, okay, or just standard error, is the standard deviation of the error term. So all of our error we were dealing with is the standard deviation of that. Now we're going to go unsquared. It's just the average distance an observation falls from the regression line in units of the dependent variable. So in this case, dollars. So think of the standard error as sort of the average distance the data falls from the regression line. So since MSE is S squared, the standard error is just the square root of it. Okay, just a square root. S is the square root of MSE, which means it's also the square root of sum squares due to error divided by n minus 2. Now we have all these numbers. We've already done them, so this is not anything complicated. The MSE, if you look at the output we had before, is 7.5187. And that actually comes out to be, when we do the square root of that, is 2.742. And we have seen that before. Now you could also do it using the SSE over here on the right. Remember our SSE was like 30.07, something like that. We could do 30.07 and whatever the number is, divided by n, which in this case is 6. We have 6 observations. 6 minus 2 is 4. So 30 point whatever else divided by 4, take the square root, we'll get the same thing. Doesn't matter, it's just some simple algebra. So the average distance in the data points from the fitted line is about $2.74. So we have a regression line, and the average distance of the points from that regression line is about $2.74. So it's the standard error of the estimate or the standard error. So you can think of S as a measure of how well the regression line, the regression model, makes predictions. So think about it. If the standard error is very large, then when we go to make a prediction for in this case, like a specific bill amount, then because the error is so wide, it's not going to make a very good prediction because the error is so high. If the error is very narrow and low, then it'll be very good at making predictions. So you can think of it as a measure of how well the regression line or the regression model makes predictions. And we can use those to make prediction intervals, which we'll do in later videos. So let's go ahead and make sense of this output that we saw earlier and kind of align it with what we've done up to this point. So number one, we have SSE, or sum of squares due to error, 30.07489. And there you can see it here on the right, and then in the output over there on the left. Now remember, we calculated this visually by actually taking the residuals, squaring them into squares, and then adding the area of the squares, the yellow squares, remember? It came out to 30.07489. We also did that using Excel, using the few columns of data, added them up, 30.07489, and there it is in the regression output here that we did in the software package. Same thing, but now you know where it comes from. Number two, mean square error. So remember that is just SSC divided by n minus 2 in this case because of the degrees of freedom. Now you see the 4 over here on the left for degrees of freedom? That's the 6 minus 2 over here on the right. So you can see how those are related. And of course we get an MSE of 7.5187. And again, that is the mean square error that is evident here in the output on the left. So again, we did it by hand and here in the software. So then we have the standard error, or in this case, it's called the root mean square error. Same thing. So it's just the square root of the mean square error. So square root of 7.5187 is 2.742. And there you can see that they're over here on the right by hand, and you can see it in the output over here on the left. So now all this output that you get when you do a regression in software, now here on the right, you see where it comes from. Not only that, you see where it comes from visually, looking at your data and looking at a graph and actually doing squares and adding them up. So what about R squared? So we have this term called R squared, and it is the measure of the variability explained by the model. And we did this before, I believe, but it's just the sum of the squares due to regression divided by the total sum of squares. So total sum of squares we already did in this case, which was 120. We found the SSE, sum of squares due to error, in the previous couple slides was 30 point something. Well, whatever is left, that is the sum of squares explained by the regression model itself. So 120 minus 30 is about 90-ish. So when we go ahead and do that, you can see here in the output that we have the model sum of squares of 89.92511. Then we have the error in total there. So we go ahead and do that division. So 89.92511 divided by 120 gives us 0.749 and some change. And then when you look at the output, you can see that the R squared is indeed 0.749376. So that's where that comes from. So R squared is simply sum of squares due to the model or regression divided by the total sum of squares, and that gives you the actual R squared that you see in your output. So remember that this helps explain how well the equation fits our data and what we can attribute to error and what we can attribute to the model. So this is where regression looks a lot like ANOVA. So the total sum of squares is actually partitioned or split into SSE and SSR, just like that. So in this case, we had sum of squares due to regression was 89.925. The residual or error sum of squares was 30.074-ish. And that is how the 120 total sum of squares was partitioned, okay, or split between the model and the error. Then when we do that, in terms of using the ANOVA table you get, we have an F value of 11.96. That will give us our significance value over here on the right. And remember, we usually use 0.05 as our threshold. So in this case, our model is significant. Okay, and that's how we would interpret that. However, I want you to understand where it all comes from. Then we go ahead and use the F distribution to go ahead and find the significance level in that. This video is brought to you by the Great Courses Plus, where you can get unlimited access to over 10,000 different video lectures taught by award-winning professors from the Ivy League and other top schools around the world. You can learn about anything that interests you: science, literature, and yes, statistics, like this lecture from Professor Michael Starbird called Real Estate, Accounting for Value, from his course, Meaning from Data, Statistics Made Clear. And right now, the Great Courses Plus is offering my viewers a free trial and is also now optimized for Australia and the UK. So go to thegreatcoursesplus.com/Brandon Foltz, my name, to have access to the 10,000 video lecture library, or click on the link in the description below. Okay, so that wraps up our video on simple linear regression, understanding model error, where it comes from, how we can visualize it, see it, understand it, what we look at the output, know where the numbers come from, how they're related, and then how we can use that to understand how good our model is by attributing our sum of squares to error in the model itself, and of course understanding where total sum of squares comes from. So I hope you found this helpful in understanding a bit more about regression and what's actually going on and understanding it and being able to explain it. So I hope you found it valuable. I look forward to seeing you in our next video. Thanks for watching.